So in this video, we actually will see how we will be able to provide approximate solutions to the MDP problems that we have specified via the definition of the optimality, Bellman optimality recursions. As we've seen from the recycling kind of robot, we have nonlinear equations to solve. Exhaustive search can be used for these solving nonlinear equations. However, they're extremely expensive and completely infeasible to solve such equations for many practical problems where the number of states and actions are usually fairly large. And therefore, even for small problems, the number of states are exploding, and therefore it is kind of, we need to come up to some approximations. So we actually look here at two algorithms which are very, I will call it, popular to solve these type of problems. So the first is called policy iteration, and the other is actually called value iteration. So both of them are used extensively for solving these problems. We'll go through each one of them. As we will see, those algorithms are kind of contain very familiar to us steps like the prediction step. And this actually is shown here, where it shows the block diagram focused on the policy iteration, which is actually a kind of fairly key algorithm to kind of understand. It involves the policy evaluation. So given a policy, we are evaluating it in terms of producing, let's say, the value function for, let's say, all the states of the problem. And we are obviously using the iterative policy evaluation scheme that we have already seen. And then what we do is and this is where the approximation is we are taking a greedy step over here to produce a new improved, hopefully, policy. And the first step was prediction step, as we discussed. Now the second step is going to be called the control step, because effectively we are controlling the policy on that step by changing it. Okay, and that's basically, it's a heuristic that we are using. The greedy approach is the kind of a heuristic approach we are using. And in terms of what is really happening, I think it's always a good idea to have this kind of contraction in our mind, where we start with some kind of initial values of value function and an initial kind of policy. We are evaluating this policy and therefore produce another VPI for that specific kind of policy. After we take a greedy kind of step, we move into a new policy that we have to evaluate again. And so the whole thing is kind of repeated, and it actually can be shown that ultimately will end up in both the desired V star and the associated pi star. And I think it's an example will actually help us understand the second part, the control part, what exactly this control part is doing. And that example that I want to use is the example from the kind of a grid world. All right, so we have the usual grid world that we have seen also during policy evaluation with the associated, if you like, Python code, and as we have seen, it's exactly the same kind of problem. We have a random policy, equiprobable random policy over here with 4 possible actions. And we already have seen the starting state. We already have seen the complete sort of convergence via this kind of iterative approach to iterative value function evaluation. Over here, we are starting from the sort of all zero value function, and the starting policy, which is this equiprobable random policy. And that the second part is the new thing for us. So we already can go through and start understanding at each step of the algorithm what actually is happening. So we compute for that random policy a value function, and that is this specific kind of table. And then the second step, which is the greedy step, is kind of easily understood here. So the value functions were greedily moving, selecting actions towards states that will improve our value. So if the value is 0 and the value over here is -1, out of the 4 possible actions in this kind of state, we have selected the one that will actually move the reward, will improve the reward, and therefore it will reach, if you like, this kind of terminating kind of state, and in that where the value is actually also higher. So the greedy part is to move towards states based on the values of the values of each state, and that's basically what we do. Then now we have a new policy. That new policy will also need to be evaluated. There may be several steps that are needed to evaluate, if you like, that kind of policy. But if we are to evaluate this kind of policy, we'll end one more time, we'll actually, this new policy, again, it's a new policy. Now we have a new policy. This will actually result into this table of the value function. And this table of this value function, again, by selecting the greedy approach, so compare where we were. Over here, you notice that we were in this new policy still at the equiprobable state. Over here, we have -2. This -2 will have 2 possible actions that are optimal to move to greedily to this state or to this state where the value is -1.7. Okay, so we are selecting, if you like, the actions that it will be the will actually be the ones will give us the largest possible value as far as this state is concerned, and that is basically the 2 actions that we have selected out of the 4 here. So here we have yet another new policy. So for that specific new policy, we are going to evaluate again this policy. Mind you, in some cases, there are 2 decimal digits which are going to determine the best possible actions that we are selecting in the greedy step. And because here we are presenting a single decimal digit, then the selections may not be entirely evident, but they are resolved if you are to run the actual code that we also provide the Python code of. All right, so that's a new policy, and we continue. And after a while, we observe also that the policy is not changing. Okay, and this policy has converged to what we call the optimal policy pi star. And this is basically the conclusion of the algorithm, which is actually called policy iteration. We have provided Python code for another grid world, slightly different on this one, that you can actually see on the links of this page over here in this kind of repository. And the last algorithm we'll actually see for approximate dynamic programming solutions to MDP problems, finite MDP problems, is the so-called value iteration, which is a special case of policy iteration. So in policy iteration, we already have seen in that other example over here that we had mentioned, the blocks, the grid world kind of problem, that already we have seen that the policy was obtained much earlier than an exact evaluation of the value function was available to us. So that kind of motivated the value iteration, which is, I will call it a shortcut that actually we can take. Instead of doing the the policy evaluation with all the iterations, we just do just one iteration. And despite the fact that the policy evaluation, the evaluation of the policy is not really, it is trending, but it is definitely not exact. We are able to get convergence still by exercising exactly the second step as we have seen it earlier in the policy iteration. So the second step is maintained as is, but the first step is we apply this kind of shortcut. And this is basically the what people are calling the kind of the value iteration. So the value iteration example, which in terms of Python code is provided over here, is the grid word that is also available in your textbook with slightly different kind of final rewards, but still with the same model, transition model that we see here. And we start to evaluate, if you like, iteratively the policy evaluation kind of step, as the formula is exactly the same as we have seen it earlier. So we have to solve this nonlinear equation now. This nonlinear equation is going to be solved as follows. First, we are going ahead and defining the capital P matrix. In fact, it's not really a matrix, it's a dictionary, where the values of the dictionary are basically the 11 states of the problem. We have a 3x4 world with one state being not possible to go to. So it is 11 states total. And for each of the states, we actually can specify to what state we actually can go to, what are the 3 children states that we can reach from each of the states. So from state 0, we can go to 0 with sort of this kind of probability. From state 0, we can go to 1 with this probability. And from state 0, we can go to state 4 with this probability. And if we are to take action 0, where action 0 is defined here to be, let's say, north. Similarly, we have 3 other tuplets that indicate the transitions for east, south, and west. And in general, for each row, we have 4 tuplets. And or equivalent, we have 4 matrices of 11 by 11, as we have seen in an earlier video when we defined the transition model. All right, so then we actually exercise the value iteration. As we discussed, the value iteration is going to involve just one update of the value function. So here we see the formula that of the V star as it is being exercised only for one iteration. So I is the number of iterations. It goes from 1 to 100. This is just one update of the V star based on the Q stars, which are resulting from taking and committing to a specific action. We have 4 actions, therefore we have Q star values. And then we take the maximum out of those and to determine our V star. That is the backup, Bellman optimality backup diagram we have seen also in an earlier video. Finally, we are printing that optimal policy. As we will see, despite the fact that initially our value function is not really at all close to what it will end up being, the policy has reached a point of convergence which will be extremely quick, and therefore that kind of proves the point that we don't have to have convergence of the value function. As we said, the final value function is going to be this one, but the same policy kind of continues much early. It converges very quickly and maintains the same sort of policy from let's say the 5th, 6th iteration. So this was the second algorithm that I wanted to cover, and I want to close this kind of algorithmic kind of discussion with some discussion about how you want to study a little bit about these type of algorithms. So evidently there is a lot of math involved in Markov decision processes. We started with a lot of definitions. The sort of domain is, if you like, rich, but it's worthwhile kind of paying attention initially at the definitions because without really a deep understanding of what is really going on at a foundational kind of level, it's difficult to understand how these algorithms are actually are working. So the most important is to exercise with various examples your understanding. We started with a couple of examples only. Some of them were kind of written down with a pencil and paper, but really the experimentation with actual Python code will just such as this example. So start with simple examples. In your course site, there will be other examples as well that we can experiment with. And when we go into the next topic, which is reinforcement learning, where we do not have an assumption about the full observability of the MDP, then things will actually become a little bit even more complicated than that, where we have now to learn some of the things that we wanted to, we assumed as known here in MDP.